wait. Well, we won't wait. I mean, just they will come in when they come in. Does anybody have anything they want to ask about before I start? I've got a few things I want to say, and I was hoping to kind of get done early, so maybe we could work on the stuff for Friday. How is the stuff for Friday going? Do you have any questions on it, or? Okay, all right. You good, Cece? Yeah. Okay, all right. Okay, cool. And we do have homework on Friday.
Yeah.
Okay, cool. All right. And then when did I say the quiz was? Next Monday? Yeah, is that what I said? That's what I thought. Yeah, let's check and see what I said. Because I was trying to think, what did I say?
Yeah, quiz next Monday.
Monday. Okay, good. Hello, good morning. Oh, good morning. Yeah, so next Monday, that quiz over just those basic definitions and theorems. Elegant, perfect statements is what we're shooting for. I was just asking if you had anyone had any questions on the homework for Friday, or we're gonna take some time to work on it today, ideally. Sound good?
Sounds good.
Okay, cool. All right, let's wrap up a few things here. So let's just see. This quick impromptu quiz, not karma free. What is the Archimedean principle? Just take a second. Can you write it down? Because you're gonna write it down next Monday. Why not practice today? Let's warm up. Because I'm about to use it. I just have a little fun. I think you got it, Carmen.
I looked back.
You looked?
Yeah.
Ah, okay, that's all right. Well, then you got it.
Yeah. There's BA rationals with B greater than A greater than 0, and then there exists an N in the natural numbers such that N times B minus A is greater than 1.
Yeah. So we've got B greater than A greater than 0, and I'll show you a simpler version of this too, which was actually how I was remembering it, totally equivalent. So these are reals with this condition, B lies to the right of A, always helps to have the picture, so that B minus A, notice that would be positive quantity. So Archimedean principle says there exists some natural number n such that n times that quantity B minus A is bigger than 1. Good morning. Look familiar? Cool. I want to kind of point out something here. Bigger than 1. Bigger than 1. Well, actually, I'm going to hold off because right now B and A could be any real numbers at all. But this also could be equivalently that for all positive real numbers x, there exists an n that's natural such that just make b minus a that x. These are equivalent statements. So just a nice thing, I think everybody's here. So anyway, we wanted to today at least address, and I'm going to address some stuff that's not in the book because I just have to while we're here. It seems essential that we talk about the size of the rationals versus the reals. But first, let's just talk about the denseness of the rationals in the reals. One of the things you'll have to spit back out on Monday at the quiz, right? The statement of this. And so let's practice. Well, we're just getting it for the first time theoretically today. So for any real numbers, A and B, you're going to see something very similar here with B bigger than A. Except I'm not making things positive at this point. And actually, I'm not sure we needed to even here. Actually, go back to this. That is irrelevant, because once this thing is positive, we're all good. So sorry about that. That was a superfluous thing that was completely unneeded, because these could be negative, and B could still live to the right of A. This could be -1, this could be -3. B minus A is still a positive quantity. So all good. So B lives to the right of A, like in that picture over there. There exists a P over Q in the rationals such that it lives between those two real numbers. So between any two real numbers, there's a rational number. No matter how close they are, no matter how far they are, certainly, but no matter how close you pick these two numbers, if they're not the same number, if there's space between them, a rational is in that space. So let's do a quick proof. And we're going to construct the P over Q. We're going to take the A to B. We're going to build the P over Q. There's a little detail in here that I'm going to skip, but we're going to probably believe it. And in the book, the details are. So if you really want the details for this little slick move that you're going to believe anyway, you can see how to prove it in the book. But I think we can believe it. So let A and B be real numbers. We always start off our proof by just getting our assumptions on the table. Then by the Archimedean, capital Archimedean property, there exists a natural number Q. We're going to call it Q instead of N. It's going to be this Q here when we get to it, but I'm just calling it Q. There's a natural number Q such that Q times B minus A is bigger than 1. It's funny, I was about to say something a little earlier and I realized I was incorrect in what I was saying. So this is going to go a lot better. This is going to be truthful as opposed to the lie I told myself this morning. Is this everybody cool? Just applying the Archimedean principle. Nothing weird. Got a little positive quantity here. So here's the part that I'm not going to prove that I think you'll believe. What we're saying is that, and actually let's write this again then, i.e., let's say Q times B, so I'm just distributing, minus Q times A is bigger than 1. So over here, I've got QA, and then here I've got QB. That distance is bigger than 1 unit. Now here's the part I'm going to see if I can convince you. Otherwise we'll have to prove it, and I didn't practice that part of the proof, so we'll probably have to. What I'm hoping is you'll believe it. It's actually super tedious, but
would you believe since these two are more than 1 unit apart, there is a whole number in between them? That seems kind of reasonable. Let's think here how this might be. So a whole number, let's say that QA is 2.17, so that's QA. And then over here is QB. And since these are more than 1 unit apart, it's 3 point more than 17, so 3.2 over here. Just a little bit bigger than at 1 unit apart. So in between here, what whole number exists? What whole number is inside there? 3, yeah. So 3 is inside there. And no matter how I slide these, let's just take a look here again. What if I had 101.98, and then I add more than 1 to it, so that's going to be 103, because 101.98, 102, let's do that. So this is bigger than 1 unit apart.
Would you want 103 for that?
Yes, thank you. I did. Okay, I was a little scared there. Yeah, thank you. Yeah, because I was like, oh shit, there isn't one. I didn't add more than 1 to it. So yeah, so the whole number between here is 102. Lives inside there. So if this number and this number are more than 1 unit of distance apart, there is inside here somewhere a whole number P. And that's the part that you can go read the very, very meticulous proof of. You good on that, Cormac? You feel okay on that? Yeah? Everybody, okay, cool. So, therefore, I'm not gonna write clearly, because the book says they say it's clear, but we need to demonstrate it anyway. Therefore, there exists some whole number P. So, and since, let's see, yeah, there exists some P and Z. So it's a whole integer. Could be positive, could be negative. It depends on if this is to the left of 0 or if it's to the right of 0. We don't know if that P is positive or negative. It might even be 0 if this is on one side of 0 and this is on the other. So if 0 sits in the middle, it's possible that P itself could be 0. There exists a P such that between QA, P lives. And with QB on the other side. So between QA and QB. Just like in that picture there. So I'm just writing that with an inequality. What do you think I need to do next? Divide by Q. So if I just divide by Q, notice that Q is a positive number. So if I divide by it, it doesn't flip the inequalities. Dividing by Q, we get basically the result we wanted, which was A is less than P over Q is less than B. So we produced a rational number between any two real numbers. And really the heart of this, you've got to have this Archimedean property right here. Sound okay? A question?
That's the denseness of Q.
That is the denseness of Q in the reals, yes. Yeah. So denseness is this thing that I say one set is dense in another set. So I would say that S is dense in T. If I take any two elements from T, and I'm showing this on the real line, but it kind of could be anywhere, there exists some element of S between any two of those. Cool? Yeah. Yeah? All right. let's talk a little bit about Q. So that's kind of the last major result, is that these rationals are spread everywhere. You know, that between any two numbers, there's a rational. One of your homework problems, and I'm going to give you a tip for it. So one of your homework problems is, what's wrong with this board? This is turning into that board in Clark. It's not as noisy. So one of your homework problems is that we've got two real numbers. I don't know, remember which number it is. A less than B. Show there exists a rational. So x, which is an irrational, between A and B. That's kind of going to be, it's going to fall back on this denseness, but there's a trick here. So, and I'm going to give you the hint. Has anybody actually done work on this one? It's like a trick you wouldn't think of. It's painfully not obvious, the trick. So the tip is this. Instead of using the denseness of Q to find a rational between A and B, because that's I for irrationals, by the way, just in case I hadn't made that clear. That's the irrationals. Instead of that, use the denseness of Q in R, this should say R, in R, to find a rational between A minus square root of 2 and B minus the square root of 2. And I don't want to say more, because saying more will blow it. But what do we know about the square root of 2? Rational or irrational? Irrational. Square root of 2 is irrational. So what you're going to do is you're going to find some x between these two numbers. So essentially what you've kind of done is you've taken the original A to B and you've shifted them to the left. Square root of 2. So here you got B minus square root of 2, and you got A minus square root of 2. And you're going to find an x between those. How do you get that x back between A and B now? And don't say it out loud. Don't say it out loud. Just think about it and do it. But your goal is to do this, then get x back between A and B, and argue that that x is irrational, no matter what. And from there, argue that x must be irrational. And that's kind of little proof unto itself you'll have to do. But that's like honestly the only way. Like if I had just left you with this, you would have gone mad. Seriously. It's a brutal, evil problem without this tip. So that should help with one of the homework problems. Let me talk really quickly about the size in terms of the number of rationals versus the reals. And I'm just going to do some casual talk about this, just a loose proof. And so let's see what you kind of remember maybe from logic and proof definition. A set A is countably infinite if what? What's the definition of countably infinite? Yeah, what you got? You got something?
Is that like if it's size is equivalent to the size of the reals, or it's
That's too big.
too big,
That's gonna be uncountably
so
infinite.
less than the reals.
What does that mean? What's the next infinity? So you've got,
The power set, does that have something to do with it?
things less complicated.
Alright.
What's the lowest level of infinity we can think of? The naturals. So that's a list. Anything that can be listed is the lowest order of infinity. Does that make sense? And that's kind of how I'm going to show that the reals can't be listed. You might have seen this proof at some point. So if it can be put into one-to-one correspondence with the naturals, which are these guys. And here, let's put here, i.e., it can be listed. So I could say A equals, here's the first element, here's the, with an infinite list, by the way, not just a finite list. So I could literally do this and you'd go, oh, everything's in that list somewhere. But the one-to-one correspondence here is that first element corresponds to 1. The index is literally kind of the function that gets it. So let me stop. Is that feeling okay? Let's talk about some things that are infinite. So, are countably infinite. So, the set of all even numbers is countably infinite. Why? What's the one-to-one correspondence? Yeah.
You multiply each thing by 2.
Yeah, exactly. This is 2 times 1. 2 times, so 2 times, that's 2x. 2 times 3, 2 times 4. Literally got this function, f of n is 2n. That maps from the naturals into the evens. And it's 1-to-1, and it's onto. Let me stop. So Christian, you're thinking?
Would the integers wouldn't be countably infinite because there's no place to start. Right?
Oh, I like that. What a great, awesome. I love that you're already moving there. Turns out they are.
They are.
Yeah, because all I have to do is come up with a scheme that allows me to list one and would definitely contain, so I love this. This is a great idea. Let's do it. So that they seem like they're doubly infinite or something, right? Because it's like you said, where do I start? Somebody help me with a scheme for putting all these into a list that starts, here, I'll get you going, let's start at 0.
Adding like squares, I guess, to like get rid of the sign, like square roots, like square root of.
See, I'm not sure what you're saying, but say it.
I have no idea. So you could like associate like the plus or minus.
Yeah, we definitely need to get that in there. Yeah, and you're getting so fancy with it, it's okay. Watch this, it's pretty simple. I'm gonna go -1, 1, -2, 2. I'm just gonna put the pairs. The negative and the positive, -3, 3. You can see that every one of them is in that list. Now the function that would go from here to here is kind of complicated. But do you believe every single one of the integers is in that list? Right? And I could figure out exactly where each one was if I got a fancy enough formula for it. Does that sound okay? Yeah? So in the same way, so there's the same number of integers as there are even numbers as there are natural numbers. They are all countably infinite. So if the cardinality of a set A equals the number of elements in A, and we have a special symbol for the cardinality of the naturals, and that is the symbol Aleph Null. And that's a Hebrew letter. It's like the first Hebrew letter. I'm not drawing it well. I practiced a lot last night. I'll show you my LF nulls. They're just cool. They're very magical looking. It looks like magical sigils. This is the kind of shit that got me into math anyway. I wanted to be a wizard. Settled for mathematician. So this is LF null, and it represents the first level of infinity. Now, when I say that, I'm hinting that there are more levels of infinity. There's actually an infinite number of infinities, each one with a bigger cardinality than the rest, than the previous. So let's talk about how this might be true. So first off, the cardinality of the open interval 0 to 1. So what I mean here, this is the open interval 0 to 1. And so I'm kind of curious, is that infinity? And you're shaking your head, no, definitely not. There's more. There's so much more in here than there are these, than there are integers, but let's see why. So let's assume, we're gonna do a proof by contradiction. Assume that the cardinality of 0 to 1 is LF null. In other words, I can come up with a list. It can be listed, i.e., all the numbers, all of them in the open interval 0 to 1 can be listed. And I won't leave any out of the list. So let's make a list over here. And we're going to use decimal representations, kind of like how we started this class in many ways. I'm going to use the 0 point whatever, because everything in here is a fractional number, so everything in here is like 0.32, 0.174, you know, blah, blah, blah. And some of them just, I don't know what that number is, just keeps on going. But everything in there can be written as a decimal expansion. Not always unique. We're going to kind of tuck that issue under the rug because we know that these decimal expansions aren't unique. But, you know, this, you'll believe me after this, I think, no matter what, if you've never seen this proof. So let's list all those numbers. So I'm going to make a list. The first one's going to be 0, A11, A12, A13, A14. I'll just do A15, dot, 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 dot. So that would be, what I mean here is if I had the number 0.724, and then the rest were zeros, this would be A11, this would be A12, A13. And the way these subscripts work is the first subscript is the row, and then the next subscript is the decimal place. So this is first row, first decimal place is 7. First row, second decimal place is 2. First row, third decimal place is 4. Tell me if that's making sense. So that's the first number in the list. I don't know what it is. In fact, you know, there's no way I can write these all, but the next one, we're in row 2, so it's A2, first decimal place, row 2, second decimal place, row 2, third decimal place, and if I keep doing this, I get a decimal expansion. And then I'm going to go to the third number in the list. And all this stuff, both, oh, I guess we didn't even do the rationals. That's all right. We'll get there. We kind of skipped ahead a little bit. 3, 2, 3, 3, 4, 3, 5. And then we've got A41, A42, A43. I'm done after this. A45. Dot. And then blah, blah, blah forever. So I got a list. Here's the first one. Here's the second one. Here's the third one. Fourth one. On down. So I just made a list, theoretically, of every number that's inside here. And now what I'm going to do is show that no matter what that list looks like, I can make one that's not in the list. No matter what your list, no matter how hard you tried, we can, and even though there's infinite, we can produce a number that is not in that list. So, but we can always produce a number B that is not in this list. So B is going to look something like this. It's going to be 0 point, it's going to have a first decimal, second decimal, third decimal, fourth decimal, fifth decimal point, blah, blah, blah. B is going to look something like that. And here's the game. This is a cool game. Where B sub I is not equal to A sub I. Now let's write that and let's talk about what that means. And it's probably better if I make a little example and show you what I mean. So let's say the list looked like this. It's 0.7134502, blah, blah, blah. Next one is, this is A11, A12, A13, 6222, 185, blah, blah, blah. Let's do one more, 0.0034147. And then this keeps on going. So my B is going to look like this. 0 point, any number except, because this is A11 right here. Any number except that. I'll make it 8. So it can be any number except this number, the first digit. The next one, the next digit, so this is B1, the B2 can be anything except that number, 3. The B3 can be anything except what? 3. So this is A33, this is A22. So B3 can be anything but that. Oh, let's just make it 1. And so on and so forth. So I just go through and I make a number that differs from the diagonal numbers along here. So I'm producing a number that's different from each one of these in some place. And so the claim is this. Claim B is not on this list. Let's try to convince ourselves why. And it might help to go here. Where would this number be on the list? Well, it can't be in the first place, because those don't match. It can't be in the second place, because the second decimal places don't match there. Can't be in the third, because those don't match. So this thing is not on the list because it will differ in the nth place from the nth number in the list. So it doesn't match, and it can't match any of the numbers in that list. And so I've just produced a new one, not in the list. B just stands alone. So no matter how you try to list the numbers between 0 and 1, you can't. And that shows us that there's another level of infinity. And this is called, so we'll say the cardinality of this is called C for the continuum. And it's got 2 U's in it, so that's freaking awesome. 2 U's in a row. This is the next level of infinity. So we've got Elif null And then I'm gonna put greater than here, but we've got C. So this is the lowest infinity, lowest level of infinity. This is the next level of infinity. But there's one above that, and one above that, and one above that. And it kind of goes back to what you're saying, Cormac, about power sets. But that's like a whole day's worth of discussion. But just so you know, and one of your cool things you know as a math person is that there's this endless cascade of infinities that never ends. Infinitely many, insane. That's fun. That's like a secret that we all have. That's like one of our cool math secrets that we share that no one else understands or cares about. But we care because it's so awesome. So let's do one last thing here. The cardinality of the rational numbers, which are dense in the reals, they're freaking everywhere, is LF null. There's a countable number. I can list all the rationals. There are hardly any rational numbers compared to the real numbers. So let's make a list. And we'll just do, we'll do the positives, just the positive rationals, but you'll believe me that you could do, I think you'll see it's kind of a twist on this proof, like there was on the positive negatives with the integers. So proof, this is thanks to Cantor again. Cantor did that proof, Cantor did this proof. It's called the diagonal argument. So Cantor realized you could list all the rationals if you just got fancy with it. And he made this grid like this. So in the first row, we're going to have everything with a 1 on top. In the second row, all the fractions with a 2 on top. So notice here, this is just for the positive rationals. So 2's on top. You can see the column actually is the denominator, associates with the denominator, and the row associates with the numerator. So then 3 over 1, 3 over 2, 3 over 3. I'm going to make one more row after this. 4 over 1, 4 over 2, 4 over 3, 4 over 4, 4 over 5, 4 over 6. And all this stuff continues, it continues downward. Infinite matrix of values. So Cantor said, well, let's see. I mean, it's kind of that thing that was hurting your brain, Christian, when you were like, how can you line up the integers? There's no start. Kind of feels like there's no start here, and that's what this cool trick was. He's like, well, what if we just kind of do something clever like this? And then go down, back up, over, down, and you've just unzipped them into a row. So by using this scheme, notice how it's kind of like the numerator plus the denominator on the diagonals adds up to the same thing. So these are like the things where it's 4, these all add up to 5, these add up to 3, these add up to 2. So his list would look like this: 1 over 1, comma 2 over 1, comma 1 over 2, 1 over 2, and then we go to 3 over 1, 2 over 2, 1 over 3. So now look here, adds up to 2, adds up to 3, adds up to 4, and so the next one's going to be, once you get the rhythm here, you can see there's a cool scheme. 3 over 2, 2 over 3, 1 over 4. And then the next ones will add to 6. And in this way, you could convince someone that every fraction will be in there at some point. Every positive fraction. Now, Christian, you know what I could do is I could do 1 over 1, comma, negative 1 over 1. I could put the pairs of plus and minuses and do the same game to get them all zipped up. or unzipped, I guess, in some way. So the number of rationals is countable. We can list them. We cannot list the real numbers. So what do you think the cardinality of the irrationals must be? Because we know that the reals are the rationals unioned with the irrationals. You're either rational or you're not. What must the cardinality of the irrationals be? Oh, and hold on, I got one more thing. I have to prove to you that the cardinality of the reals is the same as the cardinality of just those fractions. So last one, this is it, we gotta move to the fullness. Last claim, the cardinality of R is the same thing as the cardinality of all the fractions. Fractional decimal expansions between 0 and 1. Not just the fractions, but all of it, which is the continuum. And all I have to do is produce a one-to-one onto correspondence. So the proof is we just need a one-to-one onto map from 0 to 1 to negative infinity to infinity. And this is actually much easier to do than you might think it is. And here's what I would use. I mean, there's lots of different ways to do this, but 0 to 1. So here's the 0 to 1 interval. I just need to produce a function that outputs every real number is 1 to 1. Maybe something that looks like that, so like an arctangent shifted and scaled. So think about arctangent. Tangent. So if I have tangent of x, and here's x from minus pi over 2 to pi over 2. I want this to turn into this function over here. So the first thing I do is shift it to the right. So I'm going to shift it by pi over 2 to the right. So that's actually this function, tangent of x minus pi over 2. So shift, let me say this, right. So that graph looks like this. Now that's pi right there. And now I'm going to scale the input by 1 over pi. So the last thing I have to do to get this to go to 1 is to scale. So this thing here, if I actually say take the tangent of pi times x minus pi over 2, that turns into this graph right here. I probably should have scaled first. I think I should have scaled first. Shit. I don't know. No, that didn't. Yeah, I think that worked. Seems weird. Does anybody have a calculator on them? No? Do anybody have a phone on them?
I have a calculator.
Oh, we got phones. You have a calculator? Oh, a real calculator. Wow. Could you do the graph of my... Okay, yes. Yes, I could. Maybe I can live. I don't know. Let's see here. So tan of, how do I find pi? Oh, it's right there, huh? Okay, so pi times, how do you graph stuff?
I kind of forgot.
I don't know how to graph stuff. Let me just go to Desmos. I don't know how to use your calculator. Oh, thank you. I think I did it, because it's this little piece right in there. Yeah, cool, awesome. Yeah, thank you. Yeah, so this works. So if you graph this thing out, it looks like this. It's 1 to 1 and onto. So now we know there's the same number, which is insane. There's the same number of things in there as there are in just there. Same number of points there as there are there. And hardly any of them are rational numbers. Hardly any of them. In fact, and this is a harder fact to learn, and if you go to grad school and you take a thing called measure theory, which is like this class, just like on psychedelics, just everything's thrown out the window. Anything you had as a reference point of reality is gone, and you just think about measuring stuff, math stuff. And you don't even know a measure is like this whole abstract definition of measuring. But what you can show is that the total length of the rational numbers is 0. They add up to, like, their total length is 0. The total length of the open interval 0 to 1 is 1. So the irrationals are almost everything in there. So the irrationals take up the space. Take up almost all the space. Take up the space. And you could think of Q as just dust. It's just dust in space. So that's all I wanted to say about the rationals and the irrationals today. But just like the thing that I want you to understand is the rationals are like nothing. There's not many of them. Even though no matter what two numbers I pick, there is one between them. But there's still hardly any. They're dense in there, but they're dust. Craziness. Craziness. We will eventually get to a crazy-ass function. We will, at some point, eventually, look at a function called the Dirichlet function. And it looks like this. It spits out a 1 if the input is irrational. And it spits out a 0 if the input is rational. And what you get is a function that has this dense cloud of stuff at 1, because there's more irrationals, and then there's just nothing down here. There's just dust on the ground down here from irrationals. That's a crazy ass function. There's no continuity there. It's broken in the most broken way a function can be broken. So, that's all I wanted to say. How about we take the last 20, if we can still like function, still take the last 25 minutes to work on our homework? Does this sound cool? Thanks. Good. And I'm here to consult with you. And thank you, sir, for getting me that detail. I sat down to like write the letter, and I was like,
Wait a minute.
yeah,
Yeah.
you need to get, and I will get that out tomorrow.
No worries, no worries.
You'll be
I
out
think
tomorrow.
the first, like, 2 applications are the 1st of February, and then everything after that is kind of like either the 15th or like later on, so
And they all just kind of go into the same place, right? It's just a central, I thought there was.
most of them are the mathprograms.org. There's like 1 or 2 that you'll have to email to like,
That's fine.
yeah. There's like a document though that I like kind of put like all like the places for submission. Most of them are math programs.
Cool.
If it's like an email, I threw the email in there.
Absolutely. Yeah, and you just keep me on track.
Can do.
All right, thank you.
I do think the emailed ones are the ones that are due first though.
Oh, really?
Yeah.
I saw some, I just got some email yesterday.
That one's like probably from the math program.
Okay.
Like .org, just to like submit
Okay.
it to like there. But
Okay.
I think the one for like Texas on diffie Q's is, like, I'm supposed to have my recommenders, like, email it to, like, the organizer of that. And then similarly for, like, the Santa Barbara one.
Okay. Okay, cool. And you've already given me those email addresses somewhere in our
Yeah.
correspondence. Okay.
It, in like that kind of, forwarded email of like all of the resources that I also sent it.
Got it.
Not,
Okay.
there's like a list, like a short list of all the
Okay.
things I'm looking at.
Cool.
But
I'll
I can always
email you
send
if I'm
it.
confused.
Of course. No
Yeah.
worries.
Okay.
Yeah.
Thank you. Yeah. Yeah. Cool. Awesome. Yeah, and you added the Python also to your CV.
Yep, yeah,
Good.
I threw that right in under numerical methods.
That was why that was what I wanted you to be able to say that. That was why we did it, you know?
Whether or not I feel like.
You don't have to say, just say experience in,
Yeah.
don't say proficiency.
No. I've done something.
You have. You can turn on a computer, you know how to boot
Throw
up
numbers in
Python,
there, yeah.
find the web page to run stuff.
Exactly, I can start it up.
You can ask ChatGPT to write code for
That is
you.
a very good point, yeah.